Hello everyone, welcome back to this channel. So in this video, we are going to talk about one of the most important concepts in system design, which is databases. Okay, so I think previously we already briefly talked about what are databases in the architecture video. Now we are going to talk more about what are databases, why you need it, and what are the different types of databases, and what are the actual products you could use when you design a system based on your own requirements of the product. Okay, so now first let's talk about why you need databases and what are they, right? So in previous session, we talked about the basic architecture of application or your web. Okay, so basically you have the client, which could be either a website on desktop, or it could be a mobile app, right? And also the client will send a request to load balancers, and the load balancer will route the user request to different web servers based on some routing algorithm. Okay, cool. So that's the basic architecture, right? So the web server are the ones which will do all the computing for your product, right? So for example, you could do some basic computing like, okay, so I want to store some data and in cache, and then I will later fetch it. Or you just want to do some call third-party APIs. For example, let's say you want to call OpenAI API to respond to a user's query, right? So then the query will arrive to your web server, and then your web server will just call the OpenAI server or OpenAI API to get the response, and then your web server returns the result to the client, right? So this is a basic business logic. So web server are the ones which process business logic. Okay, there's no problem here. But what if we want to store the user's interactions or the user's data, or even some internal data? Where should we store them? So let's say in the previous example, yes, the user sent us a query. And what if we want to store this query? And also after the OpenAI returns the result, what if we want to store the OpenAI's response somewhere? So maybe after several days, or maybe when user want to see the history of his queries, we can just fetch it from some place, right? So the place here is actually the database. So basically we use database to store the data either from the user or from our internal system permanently, persistently. Okay, so we store it on, for example, disks, right? Or we store it on tapes for some code data, right? But no matter where we store the data, the place to store the data permanently is called database. Okay, so here behind the web server, we actually have database. And the web server could save the data to the databases permanently. Okay, so in later time, when the user wants to get some data which we stored previously, they can just send a request to the web server, and the web server can retrieve the previous data from the databases, right? And we will not lose our data, right? So this is why we need databases. Okay, cool. And this is a very typical 3-layer architecture, right? So you have client, you have web server, which only do computing, which only do your business logic, and then we have the databases to store all your processing result or the user's requests, right? Okay, cool. So now we know what are databases, and we know what's the purpose of databases, right? So now let's talk about what are different types of databases. Okay, so there are, from very high level, there are two different typical types of databases. The first one is called relational database. Cool. Let me write it down here. Relational databases. Okay. So what are relational databases? So from the name, you can guess. Relational database means we want to store data which have relationships with each other, right? And usually it's structured data which have relationships with each other. So what are structured data? Structured data is most commonly it means you can store the data with rows and columns. So let's have an example, okay? So let's say we are building a database to store the Instagram posts data, okay? So we want to store two different data. One is the posts data. So let's say someone created a post on Instagram. We want to store it in a database, right? And we also want to store the comments for the post, right? So let's say there are 100 comments for a single post. We want to store all the 100 comments in the database too, okay? So how we design the database with relational database, okay? So for a post, usually you would think what are the fields you could have, right? So let's say here, I already write this down to save the time. Cool. So basically for a post, if you think about it, so there are some must-have fields, right? So for example, we could have post ID. So for example, let's say the post ID is 8,000. And we also have user ID, which is who created this post, right? So let's say the user ID is 10002, okay? And the post type, let's say it's a video post, okay? And the post text, let's say today is a good day, right? Creation time is basically when the user created the time, right? So it basically could be the current Unix time, which is when it's 68 something, right? And also you have media IDs, which are in this case it's a video which is attached to this post, right? So for example, it could be, let's say 8900, okay? And so in relational databases, we basically store the data in rows and columns, right? So in this case, we have 1, 2, 3, 4, 5, 6 different columns for a post. And for each post, you store it as a single row, and the different posts are in different rows, right? So this is a relational database structure, okay? And also we have post comments, right? So let's paste it here, okay? So we also have post comments here. So this is a database table to store all the posts for all the comments for posts, right? So similarly, we have comment ID, which could be 9,000, okay? And also for user ID, we could have, let's say, 2999, okay? And for post ID, which means this comment is for which post? Let's say it's for the post which we stored in the post table here, which is 8,000, okay? And for comment text, we have some text, okay? And also we have creation time, which is 168 something, okay? And also we have media IDs. For example, I could attach an image to this comment, right? So then you must attach the image ID here, which is, let's say, 8976, okay? Cool. And also for each post, there could be multiple comments, right? So here we could have more comments. So for, let's say this is from user 45000, okay? And it's also for the same post, which is 8,000. And similarly, we have some comment, we have some creation time, we also have some medias. Maybe for this comment, it's only text, so there's no media IDs. So this field is empty, okay? Cool. So this basically you store, similarly, different comments are stored in different rows of the table. And for each post comment, there are 1, 2, 3, 4, 5, 6 different columns, right? So in this case, you can see either for both posts and post comments, we structure them as structured data, right? So we break them down to different fields, very structured fields. And also for each data, they are represented as a row in the table, right? So this is how we store data in relational databases. Okay, and another important aspect of relational databases is relation, right? So basically, in this case, you can see, oh, here, the post comments have a post ID field, right? And it's an ID, right? And this ID, so how do I know the actual post content, the actual post metadata, right? It's actually stored in a different table, which is posts here. So basically, you can see here the two tables are linked together with this post ID, right? So here you can see let me change it to a different type, okay? So basically you can see the two tables are actually linked by this post ID, right? So the post ID field here points to the rows in this post table, right? So they have relation. This is why we call them relational databases, right? Cool. And also you would hear another very common name for relational databases, which is SQL databases. Okay, so why we call them SQL databases? Okay, so here SQL actually stands for Structured Query Language. So why it's called Structured Query Language? Because it's specifically designed to query structured data in relational database tables, right? So for example, I can give you an example. How does SQL look like? Okay, so let's say here we want to do some big data analytics, okay, or maybe some, so not big data analytics. Let's say we have a function, we have a feature in our app, which is to show the top 10 most commented posts which are created in the last 24 hours. So yes, so basically it means for posts which were created in the last 24 hours, what are top 10 most commented ones? Okay, so let's say we want to show a trending unit in our app which shows this. Okay, how do we query the database to get what are those top 10 posts? Okay, so for SQL query, we could, so basically for SQL query, we could write it like this. Okay, so we want to select from the tables, right? So let's say I want to select, so let's consider the fields later. So I want to select from the post table, right? Post table, let's say it's P, okay? And we want to join it with the comments table, because with join, you can see for each post, what are the comments, right? So I will not go into details of what are joins, or left joins, right joins, inner joins, outer joins. That's a very different topic, okay? So I will just write the SQL here so you can see what it look like, okay? Let's say we also want to read data from post comments, and we want to join them by post.postID equals to post comments dot post ID. Okay, and we want to get posts whose creation time is larger than the last 24 hours. Okay, cool. And we want to group by posts dot post ID, and we also want to order it by the comment count. Okay, and from the largest count to the lowest number of comment count. Okay, and here we want to select the posts dot post ID and posts dot post maybe title or something, and maybe not title, post text. Okay, and also we want to get the number for each post. We want to get the number of its comments. Okay, cool. So basically this is what a SQL looks like in order to achieve this feature. Okay, so you can see, so basically in every SQL language, no matter which database it is, usually you will see it in this format, which is select, from, join, where, group by, order by, or something similarly. Okay, so this is what a SQL language looks like. It's very structured, right? So because we query the relational databases with SQL, with structured query language, that's why we also call relational databases as SQL databases. So in future videos, if you see I'm talking about SQL databases, then I mean relational databases. If I also talk about relational databases, and it also means SQL databases. Okay, so they are equal to each other. So this is a SQL databases. Okay, so we talked about what are relational databases and why we call them relational databases. But there are also 4 very important properties for a typical relational databases, okay, or for typical SQL databases. And I believe you will hear it a lot in system design and in database world. Okay, so no matter you read about, so no matter which document you read about SQL databases, I believe you hear this concept a lot, which is called ACID, properties of SQL databases. Okay, so ACID is actually stands for 4 words. Okay, so now let's talk about these 4 properties. Cool. A stands for atom ACT. Okay, atom ACT. So this is what A stands for. So what does it mean? It means when you do some changes, when you update and either read or update your databases with several steps, okay, you would treat all the steps as a single step. Okay, so which means either all the steps will finish completely, or all the steps will be rolled back, or it seems it never happened for all the steps. Okay, so let's have an example here. Cool. So let's say we have a let's say account balances database for each user in a banking system, in a bank system. Okay, so let's say I want to transfer some money from my, let's say I have as a user I have 2 accounts. Okay, I have 2 accounts in the same bank. Okay, so now I want to transfer some money from my account A to account B. Let's say I want to transfer $1,000. Okay, so here, what are the steps here? Okay, so first, I want to get my account balance. Okay, balance A from my account A. Okay, and I also want to get balance B from my account B. Okay, now I want to transfer $100 from account A to account B, which means my balance A will decrease by $1,000. Okay, and my balance B will be increased by $1,000, right? So basically you would have 4 operations to the database. One is get my balance in my account A. The second one is get my balance in my account B. And then I update both balances, right? So for balance A, because I want to transfer out $1,000, then I minus $1,000 from balance A, okay? And for balance B, because I'm transferring $1,000 into balance B, so balance B is increased by $1,000. Okay, cool. So atomicity operations means these 4 operations should either happen all together successfully, or if there is some failure or something, none of them should happen. Okay, so let's say I get balance A, I get balance B, and then I decrease balance A by some number, but then there's some failure or something, and I never increased balance B. Okay, so when your system recovers or in some other situations, you should make sure balance A is never decreased by $1,000. So which means balance A should still be the previous number. So it seems, so from the outside view, it seems you never did any of these 4 operations. So that's what atomicity means, okay? And also in a successful case, you would have run all these 4 operations. So balance A is decreased by $1,000 and balance B is increased by $1,000, okay? So that's a successful case and there's no problem, right? So let's say there is no atomicity, then there would be a big problem, right? So for example, let's say you decrease the balance A by $1,000. If all the 4 operations are not atomic, then if there are system failure or something, you would say, oh, my balance A is decreased by $1,000, but my balance B is never increased by $1,000. So overall, I lost $1,000 in my bank, right? That doesn't make sense, and it's not correct, right? So that's why we must have this property for relational database, which is atomicity. Okay, cool. So that's what atomicity. Okay. Now, what's the second one? Okay, the second one is called consistent. Okay, consistency. So C is for consistency. Okay, cool. So what does consistency mean? Consistency means your data should always be consistent after your database operation. So let's still take this example, okay? So basically, after you do these 4 operations, consistency means in my bank, okay, especially in my account, okay, my total balance should never change, okay? So in our previous example, let's say, okay, we minus $1,000 to balance A, we increased $1,000 to balance B, but the overall money is not changed, right? My overall money so is still the previous number in both accounts, right? When you sum the balance of balance A and balance B, they should not change, right? So that's consistent, right? So let's say if after the operations, okay, after operations, let's say the sum of balance A and balance B is not the same with before, then that means it's not consistent, which is a wrong user experience, and it's a big problem for banking system, okay? So, okay, that's what consistency means. And also now let's see, we have a third property, which is I. It stands for isolation, okay? Cool. Isolation means two transactions should be isolated. So what is transaction? Transaction means one operation for the user, okay? So here in our previous example, let's say I want to transfer $1,000 from my account A to my account B. This purpose or this operation is called one transaction, right? And one transaction is composed under the hood. It's composed of 4 database operations, right? Yes, but even we have 4 database operations, but from the user's perspective, from the caller's perspective, from the caller of the database perspective, it's one transaction, okay? So for isolation, it means 2 transactions should not interfere with each other. They should be isolated. So let's say, okay, I have 2 transactions now, okay? The first transaction is still this one, is I transfer, okay? Let's write this down to make it more clear, okay? So this transaction A, transaction 1 is transfer $1,000 from my account A to my account B, okay? So this is transaction 1, okay? Cool. And this in order to achieve this transaction 1, we have these 4 database operations, okay? Cool. And at the same time, maybe in a different tab or a different section of my mobile app, I also send another request, which is a different transaction. So it's get total balance from all my accounts, okay? So this is a transaction 2. Okay, let's say I send out these 2 transaction requests at the same time, okay? So how do you do transaction 2 with database operations? So basically it means you want to get balance A, get balance B, and then you sum balance A and balance B, right? And you return this balance A plus balance B to the user, so the user can know the total balances across the 2 accounts, right? Okay, so these are 2 different transactions. Let's say they operate at the same, they are sent out at the same time. Isolation means transaction 1 should not affect transaction 2's result. Transaction 2 should not interfere with transaction 1's result. And in other words, so yeah, even the 2 transactions are sent out at the same time, but from the caller's view, from the user's view. So it seems the 2 transactions are actually performed sequentially. So for example, from either I would see the result, which is transaction 1 is done, and then I perform transaction 2. Or the result could be I did transaction 2 first, and then now I perform transaction 1. So it should never have some intermediate state. So what is intermediate state? Let's have an example, okay? So let's say the 2 transactions are not isolated. So let's say we did transaction 1. We get balance A. We get balance B, okay? And now I minus balance A by $1,000, okay? Let's say before we increase the balance B, transaction 2 begins, okay? So now I get balance A. So please note balance A is actually decreased by $1,000, okay? Because you already performed balance A minus $1,000 here in transaction 1, okay? And now transaction 2 continues, which is get balance B. So balance B is not changed yet, right? And then you return for transaction 2, it continues. So it will return balance A plus balance B. But there is a big problem here, right? So balance A is already decreased by $1,000. So from the so across these two accounts, you would see the user will see, oh, actually my account lost $1,000, right? Which is a weird and wrong user experience, right? So the reason is because these two transactions interfere with each other, right? So with the correct isolation is that you should perform this transaction 1 first completely, and then you do transaction 2. So before the balance B plus $1,000 is completed, you will never run transaction 2, okay? So they will run sequentially. Another possibility is that you would run transaction 2 first, which is you get balance A and you get balance B, and you return balance A plus balance B. Only after these 3 operations are done, then you begin transaction 1. And so this is what isolation means, right? So the 2 transactions should be totally isolated with each other. So, okay, so this is the concept of isolation, okay? Now we also have the last property, which is D in the ACID, right? D means durability. Okay, this means no matter what operations I take, the results, the final result, should be stored persistently, permanently in the database. So you should store it on disks or tapes or any other places, right? So it will never be lost. So let's say you have power outage or you have earthquake or something, okay? Or maybe some of your disks are broken. You should make sure my data are always there. I can always read it later, right? So the data are durable, okay? So that's what durability means. Okay, so let's have a retrospect of this video, okay? So we talked about why we need databases and what are the 3-layer or 3-tier architecture of a web should look like with databases, right? And also we talked about the first type of databases, which is relational databases. And it's also called SQL databases, right? And we also talked about what is SQL. And we also have an example of how you use SQL to query your database for a specific feature of your website or your mobile app, right? And lastly, we talked about very commonly mentioned properties of a SQL database, which is ACID. They are atomicity, consistency, isolation, and durability. Okay, so before we finish this lesson, I also want to point out some commonly used SQL databases so you can read more about them. And when you design your system, and if you indeed need a relational databases, especially if you are storing some user information such as their username, user password, hash, and also some other post metadata, mostly you want to use SQL databases, okay? So the commonly used SQL databases include MySQL, SQLite, and also Postgres. Okay, cool. So There are also other kinds of databases. For example, in cloud environment, for example, in AWS, they have AWS RDS, which is AWS relational database. Okay, but you can read more about it. But the mostly commonly used ones are MySQL, SQLite, and Postgres. Okay, so this is about this video. In next video, we are going to talk about the second type of database, which is non-SQL databases or non-relational databases. Okay, cool. So thank you for watching this video. Hopefully you learned something. So, and don't forget to subscribe to my channel to support me, and I really appreciate that. Thank you.